Alright, THS Chem Team, here's another installment of video notes coming at you. This one is involving gases specifically, so it's going to be an advancement on states of matter and just taking a look a little more in depth at just gases. This is just going to be an intro into gases. We will actually bring up gases quite a bit more later on in the year. So let's go ahead and get started. First off, kinetic molecular theory. We've already talked about the kinetic theory of matter and saying that all particles are in constant motion. It doesn't matter if it's a solid, liquid, or gas, but a gas has some unique parts to the kinetic molecular theory that are just for gas particles. And here they are. So some of these things we don't really think about because gases, we don't see too many of them. Most of them are invisible to us, but all gases do have a mass, even though that value is very small. So even all the way down to helium, which we fill our balloons with, and it floats away, that technically still has a mass. Gases contain particles that are in constant straight line motion. So the key there with this one is that we're talking about straight line motion. And that means that they're not going to move in a curve. They're always going to move perfectly straight until they hit something. Gas particles are separated by relatively great distances. So what that means is that since they're so small, any distance between them is going to be pretty large. So think to the simulations that we looked at in class. There's a lot of space between them, especially compared to a liquid or a solid. So since there is so much space between them, the actual volume of the atom or molecule itself compared to the total volume of the gas is negligible. That means we don't worry about the volume of the individual particle. We're going to look at just the container. Gas particles do not attract one another. So since they are so small and they're moving around so quickly, they're not going to be affected by each other's motion unless they specifically run into each other or collide with one another, which actually builds into the last part of our theory, that collisions are perfectly elastic. So what that tells us is that when they actually bounce off something, that they're going a specific speed. When they bounce off of an object or another atom, they're going to keep going that same speed. So the way to affect their speed is with temperature, but not with collisions. So the collisions are perfectly elastic. So here are some properties that come with gases due to that kinetic molecular theory of a gas. Some of these are kind of repeats of what we just looked at, but gases have mass. They're easily compressible, and what that means, if you want to think of like a balloon, you can push on it and make the balloon smaller. So compressible means that you can actually force it into a smaller volume. Gases, next one here, gases completely fill the container. So that's where we said it does not have a definite shape or volume. Wherever you put a gas, it will spread out completely until it takes up the entire space of the container. Next, different gases can diffuse through each other rapidly. So that means that they can mix with each other quickly. Gases exert pressure. Again, go back to the simulations that we looked at in class. The gases are bouncing around off all the walls of the container. They're going to exert a pressure or a force on the walls of the container. The next one, the pressure of a gas depends on its temperature. Again, go back to the simulations that we looked at in class. If we increase the temperature of the gas and the particles started to move faster, they would start to bounce more, and that pressure gauge went up eventually until the container couldn't hold it anymore. And lastly, this is a review, but the average kinetic energy of a gas depends on the temperature. And we know that when we talk about average kinetic energy of a substance, we are talking about the temperature of that substance. Measuring gases at STP, we're going to see this STP notation come up quite a bit, and what that stands for is standard temperature and pressure. And this is one of the first things that you see on your reference table right on page 1, are standard temperature or standard pressures. And so this is the standard temperature and pressure are the pressures and temperatures that we would want under standard conditions so that we can get valid measurements or hold values constant and just look at one variable. Pressure is a new one that we're going to start to look at, and that is measured in a new unit we haven't seen yet, but that's in atmospheres primarily. And so if you are at sea level, you are under 1 atmosphere of pressure, and then the amount of pressures can vary in atmospheres. Some other measurements you will see with pressure are millimeters of mercury and kPa. kPa stands for kilopascals. So the two most common ones are atmospheres and kilopascals. And the conversion between them is 1 atmosphere equals 101.3 kilopascals. And all of this is on your reference table, the front page. Temperature. Now we talked about the fact that we're going to be using a lot of Kelvin. And when we are doing anything with gases specifically, you cannot use the Celsius scale. Everything has to be converted to Kelvin. So that means if you ever are given Celsius, you're going to use your formula that it also is on your reference table that we talked about in class to convert to Kelvin. And the reason we do that is we don't ever want to deal with negative numbers, especially when we're talking about gases and gas laws. Volume is going to either be measured in liters or milliliters. Most often we're going to see it in liters. Alright, so let's take a look and see what this actually looks like mathematically. So the first simple formula that we're going to look at for gases is called the combined gas law. And the way that it works out is that it's set up as a proportion. And this is also on the last page of your reference table, but it's set up as P1 V1 over T1 equals PT or P2 V2 over T2. And so what this is it's showing that if we change the variables of a gas, that we can figure out what a missing piece is. So the P1 V1 T1 represents all the variables at the start of a situation. The ones on the right with the 2's, the P2, V2, and T2, all represent what happens when we change conditions, so what we're actually changing to. So you could also look at it as initial on the left and final on the right. So our pressure, volume, and temperature initial, or 1, is equal to your pressure, volume, and temperature final, or 2, on the right hand side. So let's take a look and see what this looks like with actual numbers. A sample of helium gas has a volume of 18 liters and a pressure of 0.8 atmospheres and a temperature of 298 Kelvin. What is the new temperature of the gas at a volume of 9 liters and a pressure of 3.2 atmospheres? So in the problem, we are changing variables. So once we know that we're changing variables, that tells us we can use that combined gas law that we had just set up. So you're going to have the initial values to start with. So we're going to start with by finding all of our pieces here. So we have a V1 that is equal to 18 liters. We have a P1 which is 0.8 atmospheres. We have a T1 that is 298 Kelvin. And then we're trying to find what is our new temperature. So we're looking for, trying to solve, what is our T2? That's going to be our missing variable. That means we should have the other two variables in our problem. So V2 in this case is going to be 9 liters, so we're decreasing our volume. P2 is increased to 3.2 atmospheres. Alright, so once you have this, we're going to plug them into our equation that we had just set up and solve. So if we plug those into our equation, we end up with 0.8 times 18 over 298 equals to 3.2 times 9 over T2. Now the reason we could set up this proportion is that all the units on the left side are the same as the units on the right side. So that means our starting unit for pressure is in atmospheres and our ending unit for pressure is in atmospheres. So whatever your unit is over on the left side has to be this match up to the same unit on the right side. Otherwise, if it doesn't, you need to do a conversion. So if you have an atmospheres on the left side and a kilopascals on the right side, you would have to convert one of those so that they are the same unit on both sides. But once you get to this point and you've plugged it into your equation, now it comes down to you need to cross multiply and divide so that you can isolate and solve for your T2 variable. So you're going to cross multiply, which ends up, once you cross multiply everything through, you get 14.4 T2 equals 8,582.4. And now your last step would be to divide. So divide both sides by 14.4. So we cancel out on this side, and that tells us that our T2, once you complete all of your calculations, ends up being 596, and our temperature is going to be measured in Kelvin as long as we have kept track of all of our units and everything is maintained. So even though that is a very high temperature, that is the correct answer. So don't get thrown off if you see a very high temperature in Kelvin. That tends to happen, especially when we're using gas laws. Alright, here's the one problem I would like you to set up and see if you can put all the variables in the right place and solve for the new temperature. Good luck and bring questions to class. We will build upon this in class.